Master of Ceremonies for this track. So I'm going to be very brief and introduce Nilanjan, who's come here from Berlin, from Typesafe, and you're going to be talking about big data or fast data.
Let's see.
Nilanjan.
Thanks.
Have a round of applause for Nilanjan, please.
I'm actually not sure what I'm going to talk about though, so I'm really out of my comfort zone here. I'm really not sure why lots of people of you showed up here. I'm not sure. We'll see how it goes. So this idea about is something that I'm investing a lot this year, especially looking into a space where lots of people solving this type of problems, where the speed is your issue. Okay, and then this presentation is going to be essentially giving you an idea about that space and how that space is really evolving. Okay, and when I get excited, I tend to speak really fast. So please stop me and ask me lots of questions. If you don't ask me questions, we'll be done in 10 minutes. Okay? So let's define some terms here so that we can all be on the same page here. Big data. Who can go for it? What is big data?
Oswald.
All right, what else?
It's a combination of variety, velocity, and volume, and all other buzzwords that IBM usually tends to add. And no one able to handle that.
No one able to, okay. All right, unmanageable data. The size of the data is unmanageable. Who else?
Not structured.
Big data, abstract.
No, not structured. Structured data.
Okay, unstructured data.
Unstructured.
What
yeah.
else? Okay, yes, you guys are almost there in the same group here. Big data is a buzzword, right? Who said that buzzword? Buzzword for collecting, aggregating, and making lots of money out of it. That's what big data stands for, okay? So that's the space here, okay? And if you ask, lots of people ask this, what's the number? What's the size of the data? 100 plus terabytes of data, let's say, okay? I personally think only a handful of companies have this problem. Okay? These are the Googles and Twitters and Facebooks of the world. Okay? Now for others out there, this is the space that's evolving. Okay? Fast data. What is fast data? Where speed is important for you. Okay? Where speed is important, you want to do real-time analytics to save or make money. Okay? So our presentation here is going to be a little bit abstract, okay? Because the space is evolving. No, yes, go ahead.
I have a simple question about fast data. Probably it's also data that you can persist because it's in a very high volume, and you should transform the data on the fly. Otherwise, you will lose the data that will came just after this part of data.
Right. So another characteristic of fast data, very good. He identified is that it's a stream of data coming in at the real time. Okay, so you read the data. If you can't read that data, there is a high chances of faults happening, right? You lose that data because it's not stored anywhere. So the idea here is that, or essentially my presentations here is going to focus on this space here and how people, the rest of us, rest of the company, rest of everybody is kind of solving this problem. But behind this, there isn't a big idea here. What is? I believe eventually we all going to become a data engineer. Okay? We've been I personally looking into this space from sidelines, to be honest with you. That's why I'm completely out of comfort zone here. Okay? And watching this space evolve. But what's happening, what's reality is changing so fast that it's becoming almost important for any programmers out there to kind of learn this space. Okay? Eventually all we're going to be, like what's programming is essentially about managing data, right? And we're going to change the size of it a little bit, and we're going to make it really fast. We're going to say, we want to do this information in real time. Okay? So let's take a back step here and look at the big picture. Okay? What does it mean when you say, I want to solve a data problem here? Okay, I'm going to start saying fast/medium-sized data. Okay? Essentially, all are driven by business at some point, right? So business starts with a problem. Hey, I have this click stream happening, or I just deployed a feature out there. I want to see how that feature is doing. This is good for management because you want to make decisions based on data. Makes sense, right? I want to base my decision based on all the data I collect and figure out whether this is working for us. So that's the problem, okay? Then a group of, it could be a collection of team, engineers, scientists, data scientists, all comes together and kind of model this, okay? How can we slice and dice this unstructured data, okay? Then you fit in this model, and this is the space we're gonna look at here, okay? And to some sort of data processing pipeline, we don't know what it is yet, okay? Some sort of pipeline where the stream of data coming in, okay, clicks happening, a network logs happening, something is happening, all these events are flowing through this pipeline system, okay, so that you can produce something fast, store it in cache, in memory, Redis, whatever, so that your business can consume the result, okay? Traditionally, what used to happen, this cycle used to be month or end of the week, okay? Now what businesses are saying, why should I wait for end of the week? I want it right now. I just pushed a feature in production. I want to see whether this is working, okay? So before Typesafe, I used to work for a company called Living Social, okay? The team I used to work with, the part of the team job is, how can I get users' email address? That was the goal of the entire team. What we used to do is deploy code. Sometimes we used to push code which will run in production for 2 hours because I don't know whether this will work. This screen looks really pretty, but I don't know whether the users will like it, right? This kind of decisions are becoming very common here. I want to see how it's performing. Rest of the stack is really not interesting to me at all, okay? This thing is all about resource management. Here is where typically your Hadoop yarn or Mesos, whatever the structure comes in. And beyond this is really not interesting. Our focus will be right here. Any questions? So let's look at some examples. Let's say I want to build something where I want to predict breaking news. Okay, I want to say what's going to be hot now, what's happening right now. One of the naive way to do that will be, I'll show you how we can implement this, okay, at the end of the presentation, is looking at wiki edits, okay? It's very interesting. If you see some information, something happened, wiki is a very good source of information because you'll see that page is getting edited concurrently. Multiple users are jumping and try to produce. It's amazing how much content gets added to wiki, by the way. Amazing. Anyway, so what we will do is that if we can feed in that data as it's happening to a log, so what we're going to do is that we'll take that information, that's what typically people do, dump it as fast as possible somewhere, some storage, some log event, some event source, somewhere. Then we'll put this data pipeline, we can take these events as it's happening, process them, so that maybe we can alert somebody, maybe we can alert our editors out there. So they can say, hey, let's watch out for this page because something might happen. Another possibility of this kind of architecture is detecting network intrusions, right? Wouldn't it be nice while this network events are happening, we're logging it, we can learn some machine learning algorithm on top of that, figuring out patterns that there could be some events happening, someone trying to connect to maybe someone doing a DDoS attack on us, and figure out as fast as possible. So lots of companies out there already doing it. Here is an example. Almost similar architecture, but we are mapping it to some products, some tools out there. This is a faster data analysis by Pinterest. They recently published this blog post. I think they did presentation in StrataConf in San Francisco last week as well. What they're doing is that they are monitoring what's happening in their app. Okay, users clicking, pinning something. All these events are again dumping into some sort of event log. In this case, it's Kafka. Okay. Then finally, they're running this Spark here. Spark is this data pipeline, this thing right here. Okay, running Spark there, and finally pushing into something which is fast to query. In this case, they're using something called MemSQL. Why SQL? SQL is a very interesting place in this kind of pipeline processing because here is where your data analysts will come in. They might not be programmers. right? They query data and create this nice insights and dashboards. Another interesting application of this is Netflix. Netflix is great. I love watching Netflix. So one of the things Netflix cares about is recommendation. Who now browses movies? Nobody does that anymore, right? We all are driven by who recommends something, recommendation engine. Now what they're trying to build, wouldn't it be nice if I can show you what's trending right now? But just dumping all the information, who is watching what movie right now might not be interesting to you. You might be interested on movies that people are watching you also like. So some sort of filtering as it's happening. This is how their architecture looks like. Not only one stream, what people are doing now, they're getting this multiple event stream data coming in. These are a huge size of data, okay? And going through this pipeline so that they can run machine learning algorithm on a stream of data. These are called online machine learning algorithms. So that on live data, they can come up with some recommendations. Is anyone out here actually doing something similar? Yes, what are you doing?
Don't know if I can say, but customizing ads.
Customizing ads.
Yeah. And machine learning.
Customizing ads on real time, you mean?
Yeah.
Okay. Anyone else doing similar things here? The reason I ask is because I want to learn from you. I mean, after this presentation, we should get together because this is a very, very interesting space. I want to see how others are doing it. Anybody used to raise your hand? Yes. What are you doing?
Predicting movie revenue based on Twitter. Movie revenues based on Twitter.
Oh, so whatever, if somebody recommends something on Twitter, you are using that as a recommendation engine. Okay. Now, these are all great, right? This sounds so awesome if you can implement something like this. But there are definitely some hurdles in there. So I'm going to point out some of the hurdles. Again, I would say this is a space that's actually evolving. We don't have a perfect solution yet. So one of the things, the biggest problem in this space here is this Lambda architecture. Is anyone comfortable with heard about this Lambda architecture? Typically, when you go to the organizations, you already might be having this layer up here. Okay? So your events are happening, you're putting it somewhere, and then you have this batch process that kicks in and mines this data. Typically, that's what the organizations have. When you go in and say, okay, I want to do some real-time analytics on that, or I want to run machine learning algorithm on real-time data, then typically this Lambda architecture was introduced as a patch, as a hack. Okay? So that you can, at parallel, build a speed layer. So that if this takes an hours to do, you have some sort of layer which takes minutes to perform this task. The biggest problem with this architecture is, if you want to do it, is duplication of logic. You have to implement something for batch process, then have to rewrite something which works for the speed layer as well. So we need some sort of tool which can address this problem. This is the biggest bottleneck out there, okay? Some tool which can address this. In fact, one of the recommendation out there is, as the tool evolves, that's what I think will personally happen, this will disappear. If you can have a stream doing all your work, why even have this layer at all? The second problem with this model of faster data is you have to have some sort of predictive latency, okay? And that's where things becomes really, really challenging and in fact hard, because as the size of the data grows, running computation on them going to take time. Simple math, right? Simple logic. So some of the tools that's what's coming out with this is called probabilistic data structures. What they're doing is, okay, I don't want to give you don't have to give me 100% right answer. It's okay if you have a 1% error chances there. Look at this example for it. There's Berkeley is doing some amazing work in this space. So Berkeley is working on something called BlinkDB, where you can say that, hey, I want to run a query, but I want to restrict with time. Run this query on data within 2 seconds, I want the response time. Okay? run this where I want the error percent to be 1%, 0.1%. The idea behind this is, remember, if you're not Twitter or Yahoo, you just cannot throw hardware at the problem. I'm sorry, you cannot. Because the problem with that is hardware takes money, it costs to do this stuff. So this kind of approach is becoming very interesting because you can now write query and constraint on resources. So okay, you don't have all the servers in the world or processing in the world to run this query. Okay? I'm accepting to have some errors. It's okay to have some errors. Another interesting tool that's coming in this space is something called Tachyon. Have anybody heard about this tool before? So once you go into this space where you're doing large computations and you're running on multiple nodes, you're going to get into situations where you'll have, I copy the same thing, I cache the same thing here, 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 here. What's the point? Would it be nice if I can have some layer and all these nodes can share that, some sort of shared memory? Okay? These tools are getting created or coming up with this new tools so that they can address a problem in this space. Online machine learning. So obviously, once you started collecting this data, the next thing you're going to opt for doing is that how can I run algorithms on top of that? The problem with typical algorithms is that you don't have time. You don't have time to train your algorithm. It takes a longer time to train. And second, you don't have all the data set that you want to train your algorithm. You want to come up with algorithms which can learn as it goes. So this online category, I mean, Spark is doing lots of stuff here. I'll show you an example of K-means also. Is also pushing, again, business is pushing boundaries here. We're saying, okay, how can we rewrite some of this machine learning algorithm for streaming version, where it doesn't work with all the sets that you learn within each element. And the next thing we want to create is something that helps you with building that data pipeline, okay? This is embarrassing. Okay? So somebody created a command line tool which was faster than Hadoop cluster to solve the same problem. So one of the things that I'm noticing what's happening in this space is that Hadoop is not your golden hammer anymore. It's great for solving these big data problems. For faster data is actually not the tool for you. And this definitely cannot work. I cannot write this code to do the processing. So we need a computation engine, a model, and a nice language, a DSL, which allows me to write this code. We're going to see some examples of that. Next thing, it becomes very important when you run this streaming algorithms, because most of these algorithms go to run forever, 24/7. Then it becomes very, very critical to have some sort of monitoring in place which can monitor you. And not only that, sometimes when you have this online machine learning algorithms running, you have to tweak them as it goes. So here is my wish list. And you guys have to do it for me. The wish list is this. If we really want to come up with some sort of streaming platform which kind of solves our fast data problem, it almost needs to have some of this. Okay? It has to have something that programmer friendly that we like to do. Very important. I took care of us first. Then it has to be fault tolerant. He mentioned, right? If a click stream is coming, a data is coming, is it important for you? If you don't want to lose it, then you have to start considering fault tolerance. Okay, maybe we should replicate. How should we deal with that if my socket went down or my node crashes? And it has to have this higher throughput and low latency, right? Some of the tools, and especially Hadoop, for an example, doesn't fit here at all. Maybe sometimes Commandline Tool is the right thing to do. And it has to definitely integrate with batch system, because that's why most of the companies have made some investment, right? So there's a bunch of things out there, and that streaming platform is not there. Sorry, there is nothing like that. But one tool that comes really close here is this guy called Spark Streaming, and I think this tool has enough momentum to address some of the issues that we talked about in the wish list. It almost checks on few of the things that we talked about. So what is streaming? Anyone comfortable with Spark here or no Spark here? Okay, for rest, I'm sorry, I'm not going to Spark here at all. We don't have enough time. But I will go very high level idea. If you have anything confusion, please let me know, okay? So Spark streaming, what happens here? This data line might be very obvious. So an input stream, this could be the wiki changes coming in or network logs coming in. And this is a component which does the data pipeline for us, right? A streaming platform which takes this, and the way Spark streaming works is that it splits into multiple smaller batches. And you can define the batch size. For an example, you could say all the data coming in, batch it per second. So within a second, whatever data flows through the system will be in one batch. It turns out it's perfectly fine for 80% of the application out there, 80% of the fast data application. There is batching going on. So it's really not element to element real time here. But that is okay for almost 80% of the problems out there. In fact, you can tweak the batch size also. You could say 500 milliseconds or 50 milliseconds. Then these batches goes through this Spark engine. This is our core, which allows us to do computation. That means when you send data here, this guy will take care of sending it to a cluster of node, doing all the computation, and finally you come back with the process data. This is where you typically either feed into your Redis, your memcache, or your some storage. One of the things about Spark streaming is I found it very, very useful. It allows you to integrate with a whole set of sources out there. Almost for all the sources, it has an adapter. And this project has so much momentum out there, people are jumping in and building new adapters for them. So show me the code, okay. What I'm going to do here is that we're going to go back and see if I have to implement this, how can I do that using Spark streaming? Since I'm not doing in Hadoop, it will not take an hour. What I'm going to do here is that maybe I should run the code. So I have a Node application running here, which has a nice module to kind of tap into the IRC of Wiki and get all the changes happening. Okay? So I have done that. Now I'm going to run my Spark streaming application here. I will run the application first and then go through the code. Maybe that will help a little bit how it works. Okay, so number 3 here. Okay. It's written in Node, so sometimes it works, sometimes it doesn't. Come on. There's an initial startup time. But by the way, the streaming has already started running. So that's good. So we are seeing the live wiki events edits that right now is happening. Pumping Lima, this is probably because of the whole dress thing that happened yesterday. And this is what we are doing here. I have a second of batch. So what I'm doing here is that on every batch, I'm reading the raw wiki edits and trying to figure out which one has topmost edit. Right now, we don't have, everyone has a 1. Sometimes it shows a 5 or 6, depending upon
Something great.
like I said, Node has some issues. But the great thing about it is that let's show the fault tolerance of Spark streaming here. It will automatically reconnect once that shows up here. Okay, so I'm essentially getting the source and running computation on that. I will keep it running behind the scene. And while we look at the code, is this font readable to everybody? Yes. This code example is in Scala, but I don't think the details really matters. So first thing I'm doing here is that I'm creating this the Spark context. This gives me this guy here. This guy up here. Okay. So I create that. Next thing I do here is that create the streaming context, which is this guy here. Okay. Now rest of the code, let's go through it. First thing I do is that when I create a streaming context, I create a checkpoint here. This is to do fault tolerance. Okay? If something happens while I'm reading the live stream here, save it into some location here so that I can read it back again. That's a fault tolerance in action right there. Now I'm saying, hey, a Spark streaming, I want to read all the changes from this socket running on this port. This is where I'm connecting to the node that's running there. Okay. Now this is probably line number 70 to 27 is probably the most important thing. Now what I'm doing here is that saying wiki changes that I've got here, which is an abstraction, something called dstream. Let's imagine this is a box, okay? Box with all the batches inside it. And saying, I want to take that line, the string that comes in, the string looks like this. The string looks like this here. That string here, okay? For each line of that text, I want to split it, okay? So the batch could have multiple lines in there. I'm splitting it on each line. That's why I split /n. Then I'm taking this each line, that's actually the raw string is a JSON, I'm parsing it to JSON object. This is my data processing pipeline. I'm building transformation on top of it. That's why having Scala and functional programming are so important for you. If you are hearing functional programming everywhere, this data, this big data space and fast data space will push functional programming to mainstream. Because you almost have to here. And finally, extracting out the page URL and string. First, we're starting with count 1. So every time I see a URL, I mark it as a 1. Then comes this is probably what's happening as a stream. I just cleansed my data here, essentially. Now I'm running the actual computation. What I'm doing here is that I'm saying, running a stateful operation as a stream going through. What's a stateful operation? I'm saying every time you see for a given key, which is a page URL, increment, add it. Okay, I'm reducing the number of times it's happening. So that's actually going to give you, this guy here produces this count. This count right here. If I see the same URL coming within the second. Then I see if you imagine the streaming being a sliding window, as it's going through the stream, there will be some elements that's going to fall out of the window. For those elements, I am decrementing the count. All right, because as it's moving through the window, there will be elements falling out. And finally, I said the duration of the window here is 5 minutes. So every 5 minutes window, you run this computation. And finally, I'm filtering out saying, hey, whichever element is greater than 0, if I'm building a real world, we might say greater than 5. If a document is getting edited 5 times within 5 minutes or 10 times, 20 times, then we'll consider this document to be hot. Something that we should look into. Once you do that in Spark, this is kind of very interesting. Nothing actually happened yet. I just gave my process description to this tool. Then finally, when I say start, the print is essentially printing the stuff into the console. When I finally get start, this whole process kicks in. The await termination actually never happens because it's very hard to kill a streaming application. Very, very hard. They haven't built it. The assumption of streaming application is going to run forever. But essentially, that's the idea. Any question? Comments? This is crap. Anybody?
This is cool. This is great.
This is cool. Great. Okay.
The print there is just another transformation on a string. It's not printing right there. It's adding transformation to the string. Yes?
Yeah. This is like a for each, a side effect.
Yeah. Okay.
Yeah. Okay. did show you the code, isn't it? Okay, so under the hood, what happens if we run this? What essentially happening here is the code that we you saw in my IDE there is called driver program. Okay, something that you start. What Spark does is that takes that code that you've written in a driver program, goes to cluster manager, could be anything. Okay, it's an abstraction. Hey, I have this piece of code. Can you run it in cluster for me? Okay. So what that means is that it will take, for an example, all the transformation we're doing, like a map operation, could be sent to multiple nodes here. Each of this node, what I'm saying, is essentially a JVM, a process running, that knows how to compute, run your code. Now this is, okay, this is actually very trivial. In real world, I can't read. 5 minutes for what? If I wanted to do network intuition like this, so one of the interesting things that I struggled a lot, I'm going to put all this code in GitHub, by the way, because I'm going to experiment a lot with the online machine learning algorithms, is going to look something like this. First 3 lines are pretty trivial. By the way, the localhost stream means I'm allowing Spark to run on 3 cores. Okay, usually make it star or whatever you have you. If you're running in HDFS Mesos, you specify the URL here. Anyway. Now, this is the interesting part, right? There are streaming version of algorithms that showed up in Spark recently. One of this is running k-means, right? K-means makes a lot of sense for this kind of problems, that I can take all this network access log and kind of create cluster of them. And any of that shows distance from the cluster would be something that we should look into. That is very unusual. It doesn't fit with other access model, right? But one of the biggest challenge of this, any k-means, any data scientist here maybe can give some input here, is essentially coming with the value of k.
That's always a problem with k-means.
It's always a problem, right? So most of the streaming algorithm needs to have a model that can learn as it goes. Okay, so your k can change. Today your network is accessed the way, next week it might be accessed a little differently. Right? So your algorithm needs to evolve as it runs. That's one of the biggest challenge here. The next thing about most of the streaming algorithms, especially for k-means here, I have something called half-life. That means your clusters will not stay the same. Your clusters will move, will change as the data flows through the system. This half-life means that don't give importance to the old data anymore. Consider the new ones also. So it has a decaying factor. After that, it's kind of pretty trivial. Essentially, once you create that, then you can have this training data sources. That means you now essentially have to create, maybe I should go back here. We essentially have to create 2 streams. One stream that you can feed into k-means as a training data so that you can train them. Another stream essentially where you want to predict the values on. This is your real data source, and this is the stream that helps the k-means to learn. So algorithms like this are becoming very important to solve problems in this space. All right, so why this is better? It's actually better because most of the tool out there, it's not the perfect solution though. I mean, this is another interesting space where Typesafe, as a Typesafe, you are investing some time on. Because there are certain areas obviously in Spark streaming or streaming in general, we feel like we have more experience. So why is it better? Because of this essential model, right? One of the things that is doing here is that it fits into the rest of the big data ecosystem. That's why you hear this Spark becoming so hot, popular, because it kind of integrates with everything out there. Okay, so you're building this. Another important thing is that when you write an algorithm for batch process, you can also write them for streaming. So some of this ecosystem is actually pushing the Spark across the limit here, and it's becoming popular. Any questions? That's it. Any thoughts? Anything you guys want to comment?
Just a quick comment that though claim that doing a pure functional programming in Spark is possible, then you will not be doing this in production code. Because if you do pure functional programming with the API, you will run into a situation where like one pipeline of your transformations is taking like 5 minutes, which 4 minutes is garbage collection time, unfortunately. So you have to be aware of that stuff. For example, we have like Scala check styles and things like that, and we have to turn them off in our Spark code, basically because we cannot do pure functional programming within the calculation that we do in Spark.
Yeah, so the point here is that when you do Spark and functional programming, you actually should do functional programming. But yes, the problem with that is that it's going to acquire resources. So depending upon how big job you're running,
the thing is that you have objects that will be garbage collected within your executors. You will have data flowing around your cluster, and you have to be pretty aware of that. You still have to look on not only at how your code looks, but also how it performs. And unfortunately, if you do strictly 100% pure functional program, then you will have problems. Unfortunately, this is how it looks. Sorry.
So so know your tool. What else? Yes.
With online machine learning, and you are feeding the k-means with the learning data and then with your data.
Yeah.
Can we estimate the time when the results will be accurate, proper, or because I imagine that there will be some warm-up time when the results will be completely out of the blue, and then at the same time you can tell, okay, these results are correct, or I'm happy with them. Can we estimate this time? Warm-up?
No, it's pretty hard to estimate. First of all, sometimes it's kind of difficult to actually know that your algorithm is doing correctly. I think one of the hardest thing about k-means is to find the k number. And there's ways to do that, because if you say k is million, for an example, then all the data will feel like closer to each other. So there is a number. The first thing that you have to do, even if you do streaming algorithm, figure out the k. And then rinse and repeat, essentially. I mean, this is, you might have to tweak it as it's running. So that's one of the things about this here.
I have a question.
Yes.
When you have nodes that run your application, and your application is learning, do you have any store that accumulates the value of k for each application? Do you synchronize the value around nodes? Because if not, then whenever one of your nodes will fail, your application will behave differently, and each node can have, let's say, different value for k.
Yeah, but so synchronizing, so k is part of the streaming model. So the way I was implementing that, I was passing the model around. But yes, most of the streaming going to happen is that part of the flow where you pushing the alerts, let's say, to some dashboard in memory or whatever, there will be another pipe going in to maybe HDFS or Cassandra where you're saving all this information, or a Kafka. This is very common. You read the data from Kafka, process pipeline, dump the transformation, so that another data pipeline can pick the transformation and further do cleaning on that. So it's essentially building a pipeline of processing. Yes?
I've seen that the algorithm is used for streaming
Yeah.
and for batching version of the algorithms are actually different implementations than the ones that you could use on the batch versions. So the question is, isn't that kind of shooting the foot of the whole idea of reusing the same infrastructure and the same process?
Very good point. So, I guess everybody got the question. Should I repeat? Okay. So he's saying the streaming version of algorithm does look different. It has to be different, than because it doesn't have this whole building model based on large data set. What I am pushing for is this tool's going to get better and better. That's where the momentum is. I am pushing for is that your batch, you don't have to have a batch system anymore. You have streaming always.
Well, I thought that the argument was that, have some foot in the door because some companies may have some investment in Spark or Hadoop or whatever, and doesn't mean that we tell them, okay, we will do streaming, but we will eventually throw all this money invested away anyway, or part of it, because we're going to do streaming or batching.
Not necessarily. I mean, so case streaming is as a part of an example. There is more than that. Like that way I was building the pipeline, right? Maps and flat maps and filter. Imagine that being reused in both and batch and streaming. That's a huge possibility. Not only that, you can run SQL on stream data in Spark. I can dump things into a table as the data is flowing through so that my data analysts come and query that data. So that kind of level of integration is kind of very important. But that's a good question. Anyone else? Yes, I'm sorry.
What do you think about the Apache Storm?
What?
What do you think about the Apache Storm?
A storm. I was wondering about that question. The programmer-friendly API. Remember, one of the wishlist was I think Spark's a bit storm there. The rich API set that you get with Spark is completely non-existent in Storm. And I think that's the indication of. Thank you very much.